Video 3 on probability. Okay, some notation. I've mentioned these before, so just quickly looking at them here. Intersection we talked about. Union we've talked about. Complement we've talked about. Conditional we have not talked about. Okay, so let's talk about it. So this one's interesting. Okay, conditional. Well, I did talk about it. Actually, I take it back, but it's worth mentioning again because there's a little formula that goes with it. So again, it's when you know information. So you know B has happened, or that condition must be met, and you want to know the probability that A happened. But so you have information. It's when you're given information. So you'll often see in these questions something like this in the question. Given that, blah, 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 blah. Given that B has happened, what is the probability that A has happened? So it would be, and the way you can calculate it with a formula is it's the probability of, you want the A's and B's out of the things that contain B. That's it. Okay, nice little formula, neat. I don't see it written here. It's important. Please give a read also to what mutually exclusive means. Okay, which means that both A and B does not happen at the same time. So for example, if we're all running a race, the probability that I win, the probability that you win is mutually exclusive. We can't both win. So let's not count ties. So that would be mutually exclusive. Okay. So a little example here. I like the looks of one. I like the looks of one because it already has the diagram for me. So a fair decahedral die numbered 1 through 10 is thrown and the number noted. The events A throw a square number. So 1, 4, 9 are the three possibilities. And B throw a factor of 6. So factors are 1, 2, 3, and 6 for 6. Okay, so they've done it for us. And all the other numbers that are possible is 5, 7, 8, 10. See how they kind of listed them off and put them in a little table? Very nice. So what do they want? Find the probability of A. Okay. Probability of A. Well, there's 3 of them in that little circle out of a grand total of 10 possibilities. What else they want? Want more? B. Okay, fine. B is, there's 4 things in that circle out of 10. What's the next probability they want? A intersect B, or A and B. There's only one thing that meets both those conditions. A union B. So it can be in A or in B or in both. So there's 1, 2, 3, 4, 5, 6. 6 things in both those circles. Or in other words, there's 4 things that are not in those. Easy, easy, easy. Hence show that this little formula works. Now let's see here. A union B is 0.6. A is 0.3. B is 0.4. And A intersect B is 0.1. So, easy. Woo! State with reason whether events A and B are mutually exclusive. No. Oh, with a reason. Why? Because A, or 1, is both a square number and, what's the other one they wanted? Factor of 6. Or kind of a faster way of writing it, more mathematically, is saying the probability of A intersect B is not equal to 0. In other words, that this middle part is not empty. There you go. Okay? Fun stuff, fun stuff. Okay, we talked about mutually exclusive. Now let's mention independent. This one's important. Independent, they can both happen, but they don't, the probability of A and the probability of B don't affect each other. So, for example, the probability of me getting a 7 on an exam and the probability of you getting a 7 on the exam are independent of each other. Our chances are not connected to each other unless we're cheating or some other kind of thing. But let's kind of just, for the sake of the example, that can be true. Two events, well, the two events A and B, if they're not independent, then they're dependent, which means they affect each other. Now, I don't know if they put down that little formula, but if independent, or this is a way to check it, if independent, I can't spell, then this formula is true. The probability of both happening, you can just multiply the probabilities together. You can only do this if independent. If dependent, then you're going to have to draw a diagram. I think that's the next slide or something like that. Tree diagrams work best for that. Sorry, that's me drinking tea. So let's see here what looks interesting. Well, there's only one question, so let's look at that. For these pairs of events, state whether they are mutually exclusive, independent, or neither. Oh, I see. A, throw a head on a fair coin. B, throw a prime number on a fair die. They don't affect each other, independent. B, it'll rain tomorrow. D, it is raining today. Interesting. Independent? I could debate that one, because if it's raining today, the chances that it'll rain tomorrow are higher than if it was sunny today. But they don't affect each other, so I'm going to say independent. It's hard to tell when it's these kind of examples and not as geometric, like throwing dice and stuff is easy. Throwing a prime number on a fair die and throwing an even number on the same die. Well, the probabilities don't affect each other. They have different probabilities, but it doesn't affect each other. Yeah. Anyway, I'm getting bored of that one. Is there any other questions? Ooh, look. Much more interesting. Well, let's look at 6 there. 6. It's the last one. It's got to be harder. It's a group of 50 investors that own properties in North European cities. The following Venn diagrams show how many investors own properties in Amsterdam, Brussels, Cologne, ABC. Common little trick there. They always use ABC. One of the investors is chosen at random. Find the probability that B, given that they have A. So again, like I said, probability of B given A, just use the formula. It's probability of both divided by, well, that's not both. What the heck am I writing? Divided by the probability that of the thing we know, which is we know that they have A. And the way you do it, you don't have to calculate probabilities. You can just think of it as like more like B and A and just A. So you can just count the things. So how many are in A? How many things are in A? Where's A? There. So I got 4 plus 6 plus 8 plus 3. So that's 21. So there's 21 things in A. And how many things are in A and in B? 8 and 3. So 8, 9, 10, 11. There you go. B. Probability C given A. Okay, same deal. C and A. Ugh. Probability of A. Okay. Well, how many are in A? That has not changed, 21. How many are in C and A? So C and A, there's 6 and 3. Oh, yeah. 6 and 3 are in A, so 9 out of 21. I can simplify that. I don't have to simplify it, but why not? Interpret your answers from A and B. No, I don't want to. I guess I have to. What does it mean? I'm finding in A, I'm in the probability that, I've said it, the probability that somebody owns a property in Brussels, given that they own a property in Amsterdam. I would just write that in a sentence, as a sentence. That's it. D, you are given that this probability of C, given that B is true, is 10 out of 23. And the probability that A and C is equal to 1 over 3. Why am I repeating what they've written? Calculate the remaining regions where the Venn diagram is blank. Okay. And we do know this too. It's a good piece of information. It all has us to add up to 50 if we got all the pieces there. Okay. Well, what you can do is use the formula, see if that helps at all. So this is the probability of C and B given that probability of B. And I'm just going to move so annoying. There, take that. I need space. So probability of C and B. C and B would be here and here. Okay, so it'd be 3 plus, I don't know, divided by the probability of B. So let's see if I can set this up. So let's call this X. Okay. So probability, the number of things that are in C and B is 3 plus X. The number of things that are in B are 8 plus 5 plus 3 plus X. So 16 plus X, and that'll be equal to 10 out of 23. There you go. You got a nice little formula, nice little bit of algebra there. So that'll be 69 plus 23x equals 160 plus 10x. Then I'll just work this out. So this will be subtract 10x from both sides, I get 13x, and subtract 69 from both sides, and I get 91. So x will be equal to 91 divided by 13, which, if I did it right, gives me a nice number. And again, I don't want to think. So 7. Yay! So I got 7. Okay, got that one. And then I can work out with the other bit of information the probability of A given C is equal to probability of A and C divided by probability of C. So let's see if I can solve this now. A and C is 9. And probability of C is 6 plus 3 plus what we know now, 7. So 16 plus, let's call this y. I already forgot. 16 plus y. And that's equal to 1 out of 3. Very nice. So 16 plus y equals 27. So y will be equal to 11. So we've got 11 on that one. We got 7 on that one. And then to find out the last one, I'm going to go back to this bit of information, that 50. This all has to add up to 50. So I'm just going to take 50 and subtract all those bits. So 4, 8, 3, 6, 5, 7, 11. I get them all? I think so. Leaves me with 6. There you go. Done. Very nice. Venn diagrams, nice little thing. Cute little question. Okay. Tree diagrams, I'm going to stop.